Okay, good afternoon, everybody, and welcome to today's webinar. We're talking about why SOLIDWORKS Simulation Plastic, how we can predict and avoid manufacturing defects on plastic part and injection mold. Let's have a look through the agenda today. The first topic we will quickly cover is why we need simulation and how it can help us. Then we go for the case study. The first case study, we will have a look about how we can detect manufacturing defects initially using SOLIDWORKS Plastic Standard. And then we go to the next case, which is a multiple cavity design with the advanced runner system with SOLIDWORKS, let's say Plastic Professional. And next, we definitely going to do the ROI analysis and simulation. So that could include FEA, CFD, or plastic, doesn't really matter. All right. Let's quickly have a look why we need simulation. So the basic, or let's say the traditional procedure of design and validation is starting from any 3D CAD data design. Then we building a physical prototype, and then we put it in a test performance. So if any, let's say, faults, error, and mistakes or misperformance is happening, we will not be aware of until we see in practice we do the test performance. And this procedure needs to be go back again from the first step. We have to modify our design, again building the physical prototype, and go ahead with testing again. So that's required a lot of forward and backward. Obviously, a lot of human resources, so much of a cost involved, and that could be not a very effective way. Now, we have a better procedure if we can make our testing happening virtually. In what SOLIDWORKS propose, we have the same procedure in a design. We have a 3D CAD software, which you can design it. Based on that one, we obviously can build a virtual prototype. And in a virtual environment, we can simulate the performance. With that approach, we can validate our design before, let's say, making the real prototype. This is going to save a lot of money of building a practical prototype here. So with that one, what we can say in a traditional or typical serial procedure, any concept coming with either electrical or mechanical design, then after that stage, we go to the design validation and then do the technical communication, and it's become like operative. Now, in what we have proposed in SOLIDWORKS, we can have the concept and do the design, either mechanical or electrical, and do the design validation, technical communication, and also project data management at the same time. So all of these modules are communicating directly and instantaneously together, and that's where we're saving time and money. So it's make much more sense now why we need SOLIDWORKS simulation. One of the very important things about specifically plastic is its special application and impact of change in a different stage. Well, what we can see, there are two columns here, impact of change at different stage. Part design, impact of change is huge, but it has no cost. But obviously, if a faulty design going ahead and go to the product launch, let's say stage, and you're finding the problem, then the impact and the cost is very high. So the final product with the defect on it would be very costly to get back and be corrected. So with SOLIDWORKS Plastic, we obviously can shift the problem to be detected in the product launch stage and shift it back to part design early stages. So using SOLIDWORKS Plastic Simulation, we can adjust one round of mold rework and we can have a very positive ROI or return of investment using this tool. Now let's have a look to what we have here in different, let's say, licensing structure. SOLIDWORKS Plastic is an add-on to your CAD work. Therefore, there is no standalone. What you have to do is basically you have the SOLIDWORKS CAD in any level, and any level of SOLIDWORKS Plastic can be added to that. In a standard plastic, what you can do, you can understand the initial defect on your actual application. So filling time, short shots, air traps, sink marks, multiple gates, and weld lines are the major applications we can get with SOLIDWORKS standard. Now, if we are seriously want to test a variety of things, we have to upgrade to professional. In the terms of design, we can see you have the runner, let's say, design opportunity. You can balance your runner if you have uneven parts on the same shot. We can understand the shrinkage. If we have insert or over moldings, we can do. If any CO, let's say, injection, we can understand the fiber analysis. We can have gas injection and valve gates, and we definitely can understand the cooling time. But in a premium level, we go to very advanced manufacturing feasibilities tests, such as warping and advanced cooling analysis. All right. So with that explanation, with the, let's say, level of licensing we have, let's have a look through different case studies we go. The first one, we have the model, as you can see, made of a specific, let's say, manufacturer, and we have the injection pressure of 100 megapascal. And we would like to understand the defects, such as sink marks, air traps, weld lines, and etc. Okay, let's look at the case study. Here we are, and as you can see, I do have a design. So you can see it is been imported from, let's say, any third-party results. I made my, let's say, design changes and purification of my data, and I end up with what you can see here. As we said, most of the simulations in SOLIDWORKS are add-ins, and simply you go ahead, find them out. If you have the, let's say, correct licensing, you activate it. While you're doing that, then you will get one extra tab, which give you the opportunity to look at your project and project creation. In any plastic design, the first step we have to do is to create the cavity and mold. Well, you can see auto or manual. You can go ahead. So for example, in manual, you can see we either selecting, let's say, surface or solid meshing. And from there, we understand the mesh resolution. And later on, we go ahead. So this is the cavity detected. We're going ahead. If we have inserts, runners, or cavities to be adjusted with the triangle size, you can do that. And then you will start creating mesh. So with that one, I have done this, and simply I've created my shell mesh. All right, after this point, what we need to do is to, let's say, put in the material. This is one of the very, let's say, important asset and advantage of SOLIDWORKS plastic. Well, we have a very huge library of material sorted by family type or sorted by, let's say, companies making them. So you can see by company, if I go, there are 211, let's say, companies with their product being listed in each subcategory. If I just expand, or if we're looking at the, let's say, family, again, you can see there are huge number of material with all their material properties such as viscosity, PVT, specific heat, thermal conductivity, Poisson ratio, and the information about the polymers, and the shear relaxation modules, curling module, and everything else has been listed here. That will save us a very serious time of finding material, input them in a software, and let's say quickly we can pick up. Barely I can say there are some famous material or well-known material, and we are not listing it here. Okay, so by assigning our polymer, which is here of selected PP type, and it is BASF Novolin 1100H. Okay. From this point, you can see I'm just following up the process parameters. So in SolidWorks simulation, plastic simulation standard, we can just go to the fill area. So there is no pack or there is no cooling. There is a suggestion for filling time. You definitely, based on the, let's say, dimensions we have here, this is getting automatically updated, setting up the melt temperature, mold temperature, and injection pressure limit. This is our filling setting. You can definitely put your own data here. If you have, let's say, SolidWorks simulation plastic professional and above, then there would be more settings on warping and packaging. Now, the next important step, we going to injection location. You basically can click anywhere in your CAD data, put your injection location. You might have multiple of them. Adding a location simply means you select it. Right now you can see this is where my injection location here. You can have a prediction quickly about the flow before even solving it, understand the flow distribution, and you can also ask software to automatically add more location if it's required. All right, so a quick preview of the results. Then after this point, we can go ahead, run, and get the analysis done. When it is finished, you can see variety of results happening in here, such as filling time, pressure at the end of the fill. If there is any sink mark, we can obviously see that, and it is highly recommended to go back and modify the design change and make sure due to different thicknesses, we are just eliminating more and more sink marks. So you can see weld lines can be shown also in a filling time. If I go to the air traps and weld lines here, so you can see these are the places I have to put the vents at the location. All right, so this is our first case study. The next one I would like to show you here is back to multiple cavities. So from the design stage, it's pretty straightforward. You have one part, you can mirror it against any other plane. You have an appropriate plane, and then go to the plastic. And again, we do the shells. We selecting our polymer. Well, we can see this is Asahi. And after that point, what I do have is channel design. In channel design, you obviously have a variety of options to design your cooling channel. You're designing the runner or going to runner wizard and simply answering the question, what sort of configuration you have, what are the dimensions, diameters, lengths, and etc. And software will automatically create the runner system for you. This is exactly what I've done, and we can see even in my runner how many elements I've put, what they look like, what are the diameters, and simply my runner design is fully completed. All right. Obviously, you can have more settings here, such as hot runner and say the temperature at the different indexes. We can look at the pack setting this time, and holding time right now is 4 seconds. Pure cooling time, we put 16.32. And then from that, again, this time we go for flow and pack, simply run it, and looking at the flow result again. This is the time of the filling. We can animate it and see how easy can fill the mold. And looking at the other, such as cooling time, we can understand different parts, different region, and understand the cooling time here. If it's required, again, any design changes, we have to introduce it. So the extra features we saw here is about the cooling time, any gate freeze if it's happening, and ease of fill. You can go for more advanced option, so it is not the concern of today's webinar. So what we have reviewed is basically how we can have more into the design stage and having multiple part and runner system. Obviously warpage and cooling, let's say, strategy takes more time, and if you are interested, please let us know. We are more than happy to make a demonstration on this specific one. In terms of return of investment, we had run a couple of online sessions, and this is a service we are more than happy to give you the report on based on your inputs and data you send us. But for a case study with just no scrap in any activity, 2 engineers working with an average salary of 75 and the initial investment of like $20,000 on software, we are getting the total benefits, as you can see, around $500,000 over the 3 years, and the return of investment is back to 5 months. Going more into this detail, I'm more than happy to provide you more and more information in terms of technical and commercial information. Please do not hesitate to call us if you have any further question. Thank you so much for your time and attendance. We'll see you on next session.